Welcome, Sander, to our sort of impromptu Trends in AI interviews from the trade floor at NeurIPS. Let's start first with introducing you. Can you tell us a little bit what you work on and what brought you to NeurIPS?
So I'm a research scientist at DeepMind, and I've been working mostly on generative models in various shapes and forms. So I've done a lot of work on regressive models. In the past few years, I focused more on diffusion models, which are sort of the next big thing.
They've taken off really quickly, right?
Yeah. But yeah, in general, the thread through my work in the past half a decade or so has been generative modeling.
And I think you worked a lot also on audio and
right.
images, right? One really exciting thing that hit today was your new paper. And my original question was going to be, how do these diffusion models, how do you see them working on language? But maybe you can explain a little bit the idea from your new paper.
Sure, yeah. I mean, there's a few different ways to tackle the problem of discrete inputs with diffusion models, right? Because diffusion models are kind of based around this idea of the score function, which is a gradient of the log likelihood with respect to the input. And if the input's not continuous, then how are you gonna differentiate that? And so there's been a lot of interesting work sort of trying to find discrete alternatives to diffusion, discrete processes that gradually corrupt data, and then sort of using that as a basis for generative modeling. But I thought it would be interesting to try and stay in the continuous space and sort of map everything into the continuous domain and then do continuous diffusion, which we all know and love and are familiar with, and apply that to categorical data.
So what was the trick to kind of make that work?
So there's a few tricks that kind of build on top of each other. So one challenge is how do you embed discrete tokens in a continuous space?
Using embeddings, I guess, right?
Sure, but how do you get those embeddings, right? There's a few different ways to do that. Some people have suggested, you can actually just get them from a feature learning model, from a representation learning model. You just pre-train them, and then you keep them fixed. We actually had a paper on that a while back with Robert Strudel, who interned at DeepMind. And that works. But I thought it would be nice to find a way where you can kind of jointly learn the diffusion model and the embeddings in one go, and sort of have an end-to-end training mechanism for this setup. And the interesting thing is that if you do that in a naive way, it doesn't work, because essentially when you train a diffusion model, you're training a denoising model, right? That's the task that the model solves. You give it a noisy input, and then it tries to predict the clean input. But if you're also learning the embeddings simultaneously, then the simplest thing to do for the model is to make all the embeddings the same. Because if they're all the same, then it's actually really easy to predict what the noise was. Because there's no ambiguity about which embedding you came from. And so one trick that we found was a way to train the model with cross-entropy loss rather than the standard score matching loss that people tend to use for diffusion models. So rather than sort of predicting the clean embeddings, we can actually classify, because we know that the underlying data is discrete. So there's only a finite number of possible valid predictions there. We can actually turn this into a classification problem. And then we just have a soft max again with a cross-entropy loss, like we were used to in language modeling, right? Like we do in autoregressive modeling and like we do in BERT.
Yeah.
And as a bonus, if we backpropagate this cross-entropy loss all the way to the embeddings and optimize the embeddings, you actually get the opposite problem where they grow uncontrollably. Because now the best thing for the model to do is to make the embeddings as different as possible. Right. So then, because then the noise doesn't really confuse things anymore. But we don't want that, right? We do still want to have a gradual process that sort of gradually destroys information. So you need to constrain the embeddings.
So you counterbalance that in the loss function.
Well, so not in the loss function. So that's also a nice thing, is that if the problem is uncontrollable growth, then you can just put like a normalization layer in your model, and that fixes that, and then you don't need to add any additional loss terms to take care of that. That would also be a way to do it. Like you could say, like, I'm going to put like an L2 penalty on the embeddings, and that will take care of it. But we found that just normalizing them to like force the embedding vectors to have unit norm, that works quite well. And then you can just use cross-entropy for everything, and you don't need any additional loss terms. You don't need to trade off any loss terms with scale factors or anything like that. So it's like a nice, simple way of doing things.
Yeah, and so the way I see it, I think it's a really big breakthrough of actually getting this to work. But on the other hand, you've also ended up with a model which is very much like BERT, but using diffusion, right? So what do you see as the clear sort of benefits of using diffusion models instead of masking on the way, like going forward, on the potential of these generative models?
So I think that, like, BERT, in essence, is a representation learning model, right? So people have actually tried to use that for generation as well, but it's not commonly done.
Right. There's a recent paper which kind of tries to do that, right?
Right, but it's not like it's not what BERT was originally designed to do, right? It was designed to learn contextual embeddings of tokens. Whereas this model is a generative model through and through, right? The point of it is to do generation of text sequences, but rather than doing it autoregressively, token by token, we start with a lot of noisy tokens and we iteratively refine them in parallel. So I think the comparison that makes more sense is actually to standard autoregressive language models. And that's a comparison we also make in the paper, kind of show that, look, you can use this alternative strategy of doing iterative refinement, and it works quite well. Does it work better than autoregression? I would not dare say that.
Like the generation in this setting, you're basically generating a fixed set of tokens at a time.
Yeah.
So like, how do you control the length of the generation?
That's a very good question, and that's actually a problem that we haven't really thoroughly addressed yet in the paper. So let's say that's future work. But there are a few cool things you can do. So in the previous paper that I talked about with the intern, with Coban, he actually had a nice trick where you can actually change your tokenizer to randomly insert some padding tokens now and then the model learns that it's okay to generate padding tokens now and then.
Yeah.
And so this gives you a little bit of length variation out of the box.
And if you can, I haven't checked the numbers on the paper, but can you maybe speak a bit on if there's any meaningful qualitative differences in the generation from autoregressive models versus diffusion text models in terms of, I don't know.
Yeah, I would say so. So one cool thing you can do with continuous diffusion models is classifier-free guidance, where you kind of amplify the influence of the conditioning signal. And in our case, the conditioning signal would be the prompt, right? You have a set of tokens that are given, and then you have another set of tokens that are sampled. And you can use classifier-free guidance on those given tokens to kind of ensure that the tokens that are sampled fit really well with what you've been given. That's a cool thing that we can easily do here. That you can technically do with autoregressive models as well, but it doesn't seem to work quite as well as with diffusion models.
And I mean, I'm not sure I fully understand how it works, but like in diffusion generation, you have a fixed amount of diffusion steps, right, that you run until the tokens converge into the final text that you want. So like, is that a fixed thing, or is it something that you can actually just, if you don't like the text, you can just continue to run the diffusion process? So you kind of tuning the knobs until you... Or how do you set that? Is it a fixed type of parameter?
So it's not fixed at training time, it's fixed at sampling time. So at sampling time you choose, this is my budget, this is my compute budget, this is how many forward passes through the network I can afford, and then you choose that number, and then based on that number there's kind of an optimal noise schedule that you can use. That like at each step you reduce the noise level by a certain amount. We actually learned that in this paper. We actually learned that adaptively.
You put that as an input to the process, right? There's this parameter,
right?
How you try to do it without, but it didn't work so well.
So there's like this time warping idea that we explored, where you kind of learn on the fly during training what are the noise levels that are the most meaningful? Like which noise levels should we focus training on to get the best model?
Right.
And then it turns out that if you use the same kind of weighting at sampling time, that's also really beneficial for sample quality. So you kind of have non-uniformly spaced time steps during sampling, but the spacing is learned jointly with the model. And that is also something you can, like given a number of sampling steps that you want to do, you can derive what the optimal spacing is. And then you can sample, and if there's some things that you don't like about the sample, what you cannot easily do is just say like, let's continue the process, because at that point you've kind of removed all the noise.
Yeah.
But what you can do is you can say like, oh, those tokens I don't like, I'm just going to add back some of the noise, and then just run part of the process again. That's something you could do.
I guess that links to so one of the big limitations of autoregressive models, or like one of the criticisms I've heard often, is that they don't really translate well to the in-painting, or not in-painting, but like the kind of like infilling when you have context on both sides, right? I mean, there's works that try to do that, but my understanding is that it doesn't work that well.
I think it works okay if you train the model specifically to do this kind of thing. There's a recent paper, I think, from OpenAI, or from someone who's now at OpenAI. I don't think it's actually an OpenAI paper. I would have to check where they do that, like the fill in the middle.
So, would you say like these, like the diffusion model approach to the text generation is better suited for that type of applications, or?
I don't want to make that claim, but I think what I can say is that with the diffusion model, this is supported out of the box. Right? You don't need to do anything special.
Right.
You know, if anything, you need to do something special to make it do autoregressive generation. That's something we do in the paper. We kind of upweight the importance of prefix prompts, as we call them, because that's kind of the interface that people are familiar with right now with language models by necessity. And of course, in a diffusion model, that's not a necessity anymore. But we still want the model to do really well at those prompts, because those are prompts that people are likely going to want to use.
So if I can have one last question before we close it up. I wanted you to maybe reflect or explain a little bit how you think about computational costs of, like comparing computational costs of running autoregressive text generation versus diffusion models. Like how those two things compare, and also like kind of what model sizes are comparable, and like, I feel like I don't have a good understanding of like how you.
That's a very good question, and we do try to address that a little bit in the paper as well. There's kind of two settings, right? There's training and there's sampling. So at training time, one very cool thing about autoregressive models is that so autoregressive models kind of split up the sequence into sequential conditional distributions, right? For each token, you model the distribution given all previous tokens. And the cool thing is that during training, at least with a transformer architecture, this all becomes fully parallel, and you can train on each step in the sequence, and you get a useful gradient signal from each step in the sequence. Now, in a diffusion model, this sort of sequence of steps is actually just the noise levels, right? You go from a very noisy sequence, and then you process the entire sequence in every step into a less and less noisy sequence. But you can only train on one of those steps at a time. So by definition, I think diffusion models will be less data efficient during training, because you have this higher variance objective, because you have to sample a noise level and then choose a noise level, and you can't train them all the time. So that's on the training side. I would expect that if you train an autoregressive model and a diffusion model for the same amount of time, then the diffusion model is just not going to be as good yet. And that's actually what we do in the paper for a fair comparison, is we train them the exact same amount of time. And I would expect that the diffusion model could still improve if it were given more training. So that's at training. And then there's also at sampling time. One very cool thing, again, with autoregressive models is that you can cache results from previous steps and reuse them for future sequence steps. And that means that a forward pass in a sampling step for an autoregressive model is actually a lot cheaper than the forward pass that you need to do in a sampling step for a diffusion model, which is a full pass on the full sequence. Now, of course, we have GPUs, we have TPUs that parallelize this very well, but there's still going to be a difference in cost, I think. And so that means that for a diffusion model to sort of break even in terms of sampling cost, you actually need significantly fewer sampling steps than the sequence length to kind of see any gains in performance. And I don't think with the models that we have today that's the case. Like with the models and the sampling methods that we have today, I don't think we can sort of beat autoregression, well-optimized autoregression implementation in that sense.
So we're here at NeurIPS. You dropped this paper right into NeurIPS. I think it's a pretty major step. How do you feel about this? Like, a lot of the papers here are already half a year to a year old almost, and the real action is going on archive or like.
I've got mixed feelings about that because on the one hand, this is basically a project that I've been wanting to wrap up for a long time, and I figured it has to be done before NeurIPS, because after NeurIPS, holidays and everything, I want to maybe start something new. But it ended up, of course, taking a bit longer than expected, and so it ended up landing on the first day of the conference, which wasn't intentional, but either way. But yeah, to answer your question, I think it's actually, like, for me, conferences are not so much about learning about what the papers are. I already know what the papers are. I've seen them on archive, I've seen them on Twitter. It's about talking to the people behind them and sort of discussing them with like-minded people, and then that's a really great opportunity.
Over beers and music, maybe.
Right, exactly. Yeah.
Any tips you have for people interested in NeurIPS? Kind of like what are you most excited about that is here at the conference, or what?
I'm always very excited about the workshops.
Yeah.
The workshops tend to have a bit more, fresh content, but also they tend
Late
to group
breaking
them
kind of,
like-minded people
yeah.
together, and so you can kind of go to a workshop and then be surrounded by people that are interesting to talk to, which is really.
So which workshop are you recommending?
So there's a few. So there's both physical and virtual workshops this year. There's one coming up on score-based modeling, which obviously is one that.
So it's your first time in New Orleans, or?
No, I've been here before for iClear.
Yeah.
I
Oh,
think a few years ago.
2019. I was there as well. Yeah. It drew me back at the first chance I could get. Any recommendations you have for like the social side of the conference, or sightseeing in New Orleans?
I'm not much of a planner. I'm more of a follower, so I let other people rope me into lots of cool stuff to do. But yeah, probably be doing a bunch of hanging out in the French Quarter and trying to catch some jazz and that kind of thing.
Very good. We're very much into that as well. So CD, right? Is the
That's right.
paper? The exact title is?
Continuous diffusion for categorical data.
Exactly. Continuous diffusion for categorical data, out on Archive today. Check it out. Thanks, Sander, for joining us for this interview.
My pleasure.
And
Thank you.
Thanks so much.
great meeting you, and have a nice NeurIPS.
Thanks, you too.